So let me recall that the previous lecture the following formula was proved. Is it okay to write here? The structure is the following. We take 1/3, 1, 2, 3, 4. You see. Here we take 1, 4, 3, 2. Two negative terms. R I L is G I L R J K minus R divided by 2 G I K G J L minus G LG JK. So at the previous lecture, we proved the following formula for reconstructing the Riemann tensor if n equal to 3. So if n equal to 3, then the Riemann tensor could be reconstructed in terms of the Ricci tensor and the metric calculated at this point. So it's algebraic expression. Of course, if you know Riemann metric in the neighborhood, you can reconstruct the curvature tensor. But you know the Riemann metric only at one point, not its derivative. It's algebraic formula, not including any derivative. Then the Riemann tensor is completely defined by its Ricci tensor. What happens if we have dimension greater than 2? Let's introduce one tensor, W. Okay, let me write it again here. Do you see what it's written here? A, B, C, D is R, A, B, C, D minus 1 divided by n minus 2 G, A, C, R, B, D plus G, B, D, R, A, C minus G, A, D R, B, C minus J, B, C, R, A, D. You use the same structure. For n equal to 3, we have exactly this formula. Plus 1 divided n minus 2 R JBC. So let's introduce the following tensor. We see that if n equals to 3, it's identically 0. The formula above means exactly that the term below is identically 0. But of course, if greater than 3, it's not necessary 0. Because the number of Ricci components greater than 3 is smaller than the number of independent components of the Riemann tensor. Therefore, such reconstruction formula is impossible. You could not introduce similar reconstruction formula. But what is the main property of this tensor? Hello? Okay. The main property of this tensor is that let's raise one index. Okay, let's write here. A, B, C, D is J, D alpha, W, A, B, C alpha. Let's raise one index. The statement is this tensor W is called Weyl tensor, is invariant with respect to the changing of conformal representative of the same conformal class. So it assumes it has one transformation of Riemannian metric. Tilde of x is 2 omega of x. So we multiply our Riemann metric by some scalar function. We change the metric, but we keep the same conformal class. From this point of view, we can go from the Euclidean metric to the metric of sphere or Lobachevsky plane, for example, or Lobachevsky space, because they are conformally equivalent. So we replace a metric by a conformally equivalent one. Theorem: this tensor W, this tensor, is invariant with respect to such transformations. Of course, you can raise any other index. It's not necessary to raise the last or the first. If you raise one index, you obtain conformally invariant expression. Let's check it again. I'm sorry, I will check it by a direct calculation. So let's do. First of all, let's recall the definition of curvature tensor. R in fact, I will prefer to work with this tensor. Because of symmetry properties, it's no difference which index to raise. Because it's Q-symmetric with respect to transposition AB, it's Q-symmetric with transposition of CD, and you can change these two groups. Therefore, it's no BCD. In GL, so LG, LJ minus DL gamma K IJ ijk and ijk d dxk, or maybe no. Let's prefer to use this uniform form. dj g I hope you have to know all these formulas. These formulas shall be in the course of remaining geometry. But I hope so. The formula are treated to be known. And now let's check the transformation rules. So assume that you make the following transformation of the metric tensor. You have the metric tensor. You apply the following transformation. And let's calculate the transformation of all the objects. First of all, ijk, let's calculate ijk, where ijk is First of all, let us check the following formula. But okay, let's check it. How to prove it? The proof is very straightforward. So we make the following transformation. What happens? Gamma tilde I j is 1/2 to omega. I don't write the dependence of the coordinates. It's okay. You have what you have tj g alpha k tilde alpha k is 2 tj omega to the power to omega alpha k I say, okay, I hope this formula requires no comments. So is it okay? I simply use Leibniz rule before we obtain альфа k плюс тильда альфа k. You agree? So here we obtain ijk is I alpha times d j alpha k plus, let me write dj omega plus j alpha minus the alpha j jk minus 2 the alpha omega tilde okay. Okay. If you collect white terms, you obtain this. So white terms are exactly this. You see? White terms. Okay? Okay? White terms and green terms. Okay, so let's write. S as I jk is j I alpha I agree. I again use this definition. 1/2 into I reduce g tilde alpha k alpha minus d alpha alpha omega j tilde jk. You agree. You obtain this. So, sorry, up to this moment, are any questions about this calculation? Therefore, and now this term is ik minus, and also let me introduce another notations. I hope you know it or not, but nevertheless, let me introduce it. Where to? Okay, let me use this. No, okay, let me write this. You know the derivatives with the upper indices? Or not? It's definition. Simply definition. It's convenient to use the following notation. Derivatives with upper indices. By definition, this is. It's simply a definition of the derivative with upper indices. It's nothing more than this. But what will be important if you calculate covariant derivatives? The covariant derivatives of the metric are zero. You see. And you will use it. So you see, the last term is this one. So you understand it. The derivative with upper index. So we proved this formula. Okay. This formula was proved. So now we need the second formula. Let us do it. First of all, let's prove the following formula. R tilde our next part is to prove this formula. So Lemma 1 was this. Lemma 1, this is the Lemma 2. This formula. First of all, okay, in principle, formally we can write this formula in the following way. Formally, it can be written. or it can be written the following way. So, okay, maybe let's do a fair calculation again. So, first of all, what changes? KL can be written, okay, let's write it fairly. D K dk you agree? The first term became this one minus dl gamma I k j minus dl s I k j plus gamma. Okay, let's be careful. Gamma I gamma Lj for gamma okay. Let's have a look. What do we have? First of all, let's mark this term. And these products. It will be, so first of all, it will be L plus. Plus, what do we have? Plus S I L J Y let's take this term. Okay, let's take this product. Okay, alpha S so we have three cross products. Okay, but okay, let's write these terms and then discuss. TK I K J plus K alpha J plus gamma L J alpha S I K alpha plus S I K alpha Lj minus gamma I L alpha S alpha Kj minus alpha Kj S I L alpha minus S I L alpha S alpha Kj. And we have to add extra more terms because okay, these terms are okay, you recognize them. But what is missing? We have to add extra terms. We have to obtain the derivative. We have this plus this plus this, and we need an extra term. By the way, S is tensor, you understand. S is a tensor. Gamma is not tensor, but S is a tensor. So it's in fact sense not correct to talk about covariant derivatives of gammas, but it's absolutely correct to talk about covariant derivatives of S. So we need an extra term. So let's add an extra term. The extra term will be minus gamma alpha K Just a second, let me remember a moment. Alpha. Sorry, let me have a look. No, gamma you have this term. You agree? This term, and we add this term here. And plus S I agree. We can add subtract these terms. Okay? No, they are symmetric. Therefore, if you combine this plus this minus this and minus this, these four terms provide us the covariant derivative of S. And again, if you combine this this and this, you obtain this term. You obtain this term, and here we obtain this term. So, okay, this calculation. Are there any questions about this calculation? Sorry. So, we proved this formula, and we proved this formula. By the way, my suggestion, it's a good exercise to repeat it on a piece of paper. So, okay, let me remove it, but now we proved two lemmas. We proved this lemma, and we proved this lemma. Now, we need next lemma, lemma 3. Yeah. The L omega Sn minus 2 the alpha omega. So, now let us prove the following formula. We calculate the variation of the Riemann tensor. Now let's calculate the variation of the Ricci tensor. Sorry. But you understand, it's direct calculation, but I don't know how to avoid. I think this calculation shall be done in some way. Maybe I can split to bigger number of lemmas, but I don't think it will help too much. Okay. R tilde JL is R I J I L is in R tilde. Summation by I. Nothing more. You agree? First of all, it's RGL plus delta S I LJ, you agree? Delta L S I J, you agree? J S I alpha S alpha LJ minus S I L alpha S alpha I J. You agree? You have the following formula. And we have summation by I. Let us do summation by I.
Sorry.
Here some
No, K.
I. So, okay, let's remove everything except the most necessary formulas. Okay, let me remove everything we don't require. May I remove it now? Because we don't use this formula anymore. The only formula we need is this one. We have to keep the formula in mind. It's the only formula we really need. So we have to calculate the following guy. We write it. Delta I S I L J, you agree? Minus delta L S I L plus S I alpha S alpha J minus S I L alpha S alpha I, J. Okay, you have to calculate this expression. Let's calculate. What does it? Let's first of all calculate this expression. S I alpha. Here you have summation with respect to I, of course. You remember. If you have upper indices, low indices, it means summation. So. Okay, maybe I'll remove it also. I use this part of the blackboard. Alpha is ij di alpha di omega, you agree? Plus delta I alpha. Okay. The alpha omega minus J I the I omega. You agree? Summation with respect to I. So this is the alpha omega. Agree? Agree? Sorry, is it clear here? Any questions about this calculation? Sorry, it's something wrong here. D. Sorry, I am something wrong. Sorry, I wrote something wrong. Delta I. Minus. I'm sorry. So let's write it first of all. The first term, delta I S I L J. delta I L delta I J dl omega minus di minus J Lj You see, we have these terms. Means delta L minus M delta L Okay, so is it clear with the first term? You agree? With the second term? And we have these two terms. Let's see what happens with this term. Have you obtained this? What is this? This term became delta L C J omega. You agree? J omega have used the property that the covariant derivative of the Riemannian metric and the inverse tensor is 0. Use Ricci with a property here. Understand? Okay? Now let me remark that the two terms are equal. Okay, let me write. Delta J omega is J omega minus L You agree? Is the definition of the covariant derivative. You see this expression with respect with L and J. You see? Because this is symmetric expression. Therefore, this expression is symmetric, therefore, okay. Okay, we see that we obtain by the way, if it's not symmetric, it would be incorrect, because everything should be symmetric. All objects are symmetric except this one. So it shall be symmetric. Therefore, we also prove the lemma that we prove this identity, you understand. So, any questions? I'm sorry. Okay, okay, so we obtained these two terms. These two terms. Now, what do we have to do? We expanded this to express, we obtained these quadratic derivatives, because we have two types of here. Second order derivatives and first order derivatives. Here we have second order derivatives, here have first order derivatives. We check the second order derivatives, now we have to check the first order derivatives. Okay, let me remove it. No. We did everything. Psi I alpha. What does mean psi I alpha is equal to omega delta alpha L omega plus alpha G minus G LG T alpha omega. This is this term. Now let's write this term minus LD alpha omega dl omega minus omega times delta alpha p minus okay, so we have this expression here again. Okay? Okay. Let's calculate. First term, it will be the alpha, delta alpha, n You agree? You understand the first term? To n. The first two term gives us the alpha omega plus you have 9 terms. Let's calculate all the 9 terms. But what to do? I don't know how to avoid it. This is delta by summation First of all, let's sum by this term and let us sum by I. We obtain d alpha, d L omega, dj omega. Yes, first we sum by alpha. Okay, let's sum by alpha. If you sum by alpha, you obtain dl, di omega. Dj omega. Minus the second, this product. Let's have to the second term. Second term, so by alpha, the dj alpha j alpha omega. Okay. The last term will be plus gl You agree? Okay, you understand this? Now, so the next term. The alpha I, it will be n square. Sorry. No. It will be product n, you agree? Delta I alpha. Delta alpha I. First of all, we may assume it will be n. Is it necessary to explain it? You have n square terms. N of them is equal to 1, and all others are equal to 0. Minus n alpha omega omega First, let's look the last term. What happens? First of all, we sum by I. If you sum by I, you obtain J alpha. J, you agree? Then we sum by alpha and we obtain J omega. J omega. And allow calculate this term. Plus first of all, we sum by alpha, obtain GLI, DI, DL, omega, DG, omega. Omega plus the second term will be I omega. The I omega. let me 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, let's check again. Yes, these two terms come from this. 1, 2, 3. And the last term minus okay. Minus. It's low indices, so G L omega, and this is G minus P J omega D L omega. Okay. Sorry, is it clear? Are there any questions? Okay, first of all, as for terms, so what we obtain? I agree. We have these four terms. The terms are exactly this. Okay? And then let's look to remaining terms. And this we have also this terms. This we obtain the last term. So, okay? So we proved, so what we have done. First of all, we calculated the variation of the Levi-Civita tensor under this transformation of the metric tensor. Then we calculate the deformation of Riemann tensor, the Ricci tensor, and now calculate the deformation of the scalar curvature. Last step. You have to calculate the variation of the scalar curvature. Well, let's prove the last lemma. Not lemma, but the last lemma is not theorem, but lemma. Let us prove the last lemma, R tilde. What do we have? We have that. That's 4. You agree? By definition, therefore, by definition, we have you agree? This term plus. Okay, let's let's consider to simplify notations. Let's use the formula. Let's write this way. E to the power 2 omega r tilde is r. Let's multiply it by 2 omega. GL agree. The first term minus and minus 2 J omega plus n minus 2 d alpha omega. Let's have a look. Is equal to R. This is the trace, you agree, of the unit matrix. The trace unit matrix, therefore, the alpha omega.
Sorry. First term. R is G.
Sorry.
First term.
Her. Her.
No.
Sorry.
Okay.
Minus n. Is 2. So what we obtained? So it's R. Now we combine these two terms. Minus 2 the alpha omega. Combine the remaining two terms. Minus okay. So I hope, okay, I'm sorry, it's direct calculation, but I don't know how to avoid them. In fact, I don't know how to avoid them. I have no idea. So let's do a direct calculation. Now, let's calculate transformation rule for the Weyl tensor. JKL minus and minus 2. We have to raise the first index. It's delta ABCD, maybe I'll write ABCD to A, B, C, D. Oh, no, IJKL minus delta IK R RJL IK minus R tilde JK minus Greenwich L G K tilde I L. Agree? Plus two n minus 2 R tilde Okay, so now we have to use these transformation rules. So what we have? First term we have LG minus say KG AG RGL. I think maybe it's too much for today, for one lecture. Maybe the time is over. So I suggest the following. I stop here and finish the calculations in the next lecture. What do you think? Maybe it's time for the lecture, maybe it's enough for today. But okay, I hope you have this collection of formulas. And then the next lecture we'll do calculation using this collection of formulas. But I think maybe